So MapEdit. MapEdit is a very simple and yet very popular quality diversity algorithm. It stands for multidimensional archive of phenotypic elites, and you will see that this long name actually is a quite accurate description of what this algorithm is actually doing. And it's very interesting because it's a very simple and yet extremely powerful algorithm. So I've been working on the concept of MapEdit for the last 5 years, and my experience is that every variant that try to improve the performance of this algorithm, even if it's possible to do it, they usually increase the complexity of the algorithm by a significant margin. So typically, in order to gain like 10% of improvement, the algorithm needs usually to be twice as complex as it is now. So the goal of MapEdit is to discretize the space of the BRF descriptor into a grid and to try to fill this grid. So remember the example that we used in the previous video, where we have of our hexapod here. The BRF descriptor is simply the proportion of times that each leg is in contact with the ground. So that's a 6D BRF descriptor space. And the idea is that we discretize this 6D simply by into a grid, and so here you can see the grid. And so because it's a discretization into a grid, we can easily slice it and represent it into this 2D map. So you can just imagine that every pixel here corresponds to one cell in the 6-dimensional grid. So here, the way we discretize the grid is we have 6D, each dimension is divided into 5 values, and so this means that we have 5 times 5 at the power of 6 cells in the grid, which lead to more than 50,000 cells in the grid. So the goal of MapEdit in this case would be to try to fill each of the cells of the grid in order to that's a 1. In order to find as many solutions and up to 15,000 solutions here. And so, as I said, the most important aspect of MapEdit is this grid. So it discretizes the BRF descriptor space into a number of cells. So imagine you have a 2D space. You can discretize it into 25 cells by discretizing every dimension by 5 bins, so 5 by 5 grid here. And then what is important is the addition mechanism. So when we have a new solution that we want to add in the cell, okay, so here the solution can either land into an empty cell like this one. So in this case, that's very simple. We simply add the solution in the grid. But if the solution goes into a cell that is already occupied here, so in this case, we will simply keep the best out of the 2 solutions. So only the best solution of the 2 solutions that are landing in the same cell is kept. And so typically, if my new orange solution is better, we'll discard the former one and keep the new one. So it's a very simple archive management. We simply take the BRF descriptor definition of novelty search. We discretize the space that is defined in the BRF descriptor space to turn this into a grid, and then if the cell is empty, we just add a new solution. If the cell is already occupied, we just keep the best out of the 2. So this means that it has just one parameter, that is the resolution of the grid or the number of cells. That's a big advantage because it's very easy to implement, but it has a small drawback, which is that the density of the solution is not always uniform. So typically you can see that here, for instance, we have 2 solutions that are very close to each other, while here we might have solutions that are significantly further away. So the density in this region is lower than the density in this region. In some complex application, it might be troublesome, but in general, it's a very good and simple implementation. So then, here in this slide, we have the entire pseudocode of the algorithm, and actually I don't need to have anything more complex than this because we're just following this schema here, where we initialize some solution in the grid randomly by randomly generating some random solution and adding the solution in the grid, so like those 2 solutions here. And then we enter the loop, or like the typical generation iteration of an evolutionary algorithm where we select a solution. So we randomly select one solution from the archive, so one of the two, uniformly typically in MapEdit. We apply a mutation operator. For instance, if your genotype is a set of float value, we just add Gaussian noise on some of the value or all of the values. So this will create a new solution that can be evaluated. So here you can see that the value, the color of the value of the point here that corresponds to the fitness change, but also because we change the solution, so not only, so the mutation will lead to a change in the fitness, but it's also a change in the behavioral descriptor value. So of the cell that will land, where the solution will land. So typically here you see we select these points, we mutate it, that create a new solution with a different fitness, and it will also land in a different cell. So the parent was here, and so now it's landing here. And then from there, it's just the normal archive management and cell management that I introduced in the previous slide. So if we land in a new cell, like here, we simply add the solution in the collection. And if, like in the next step, we generate a new solution that lands in an already occupied cell, like here in this case, which can be the same one, because it can happen that the mutation is not changing the behavioral descriptor, we will simply keep the best solution out of the two. And we repeat this random selection, mutation, evaluation, and addition mechanism. So that's the 4 steps that we can see here: random selection, mutation, evaluation, and addition in the archive, until a predefined number of generation, or until the coverage and the number of solution are stagnated. I will cover here the different quantifying performance that we use usually in quality diversity. So here it's a figure taken from this paper here, where we can see some example of some metrics that we can use. So what is important in quality diversity is the diversity of the solution. And so usually in order to quantify the diversity of solution, we use the archive size. So how many solutions are stored in our collection. So typically in MapEdit, it means how many cells in the grid are occupied by one solution. A second important aspect is the performance of the solution contained in the archive. So the usual metrics is either the maximal performance or the average performance of all the metrics. We can also be sometimes interested in the convergence speed. So typically if you have a solution that reaches the average performance faster than another one, that might be an interesting aspect. Usually, an important concept is the QD score here. Usually, we summarize the 3 concepts here, or the 2 main concepts of diversity and performance, into the QD score, which is defined as the sum of the fitness of all the solutions in the archive when we assume that the performance, so the fitness, is strictly positive. This means that finding a new solution that populate a new cell will benefit to increasing the QD score, because that will increase the total sum, but also replacing a solution by a better one will also increase the QD score. So having a lot of solution is good, having some very good solution is good, but having a lot of very good solution is the best. We can also note that the concept of diversity and performance can be represented as a Pareto front, so here, because there are some kind of multiple objectives that we try to optimize. And so here we can use the Pareto front in order to define which variant of the algorithm is better. But that's some advanced concept. The most important is this diversity, performance, and QD score, usually. So here I focused on MapEdit because it's a very simple algorithm, very powerful, actively used in the literature. You will see some example in a minute. But there exists a more general framework where you can use different operator and define your own quality diversity algorithm depending on the task and the challenges that you are facing. And all algorithms in this framework can use this figure and this representation, and if you want to learn more, you can refer to my paper here. So typically we can use different selectors, so in order to select different solution here, and not simply the uniform random, even if, as I told you, so that's what we use in Mapillity and it's shown to be very effective. But we can use some alternative approach, so for instance, adding a bias to select solution with a large fitness, for instance, or solutions that are novel, or a curiosity score, which is a concept that I introduced here. Again, I'm not asking, or you won't be asked in the exam to know those different elements and concepts, but it's just interesting for your own knowledge about this domain to know that more complex variant of this algorithm exists. Similarly, in Mapillity, we saw the grid archive in order to store the data, so where we discretize the space, but we can also use the unstructured archive from Novelty Search in order to have an unstructured archive that will maintain the density instead of having like a strict discretization. Again, you don't have to know the details, but it's important to know that both variants exist. There are also more advanced mutation and also crossover operator. We can define a crossover, even if it's not here, by selecting multiple solutions during the stochastic selection, and here having a crossover before the mutation operator. So that's it for Mapillity and some more advanced concepts. And here are a couple of recent examples of application of quality diversity and Mapillity more specifically. So an example that I showed during my PhD, which is that we can use actually a QD algorithm with some unstructured archive and a uniform sampling selector in order to learn this robot to learn not only to walk straightforward as fast as possible, but also to be able to walk in every direction. So here you have the robot that starts to walk, and we want to have a collection of controller, each controller moving the robot in a different direction, both forward but also backward. And so here you can see the example of the robot, of the real robot. And what is very interesting in this work is that we can wonder why the notion of quality diversity and Mapillity is so important, because if the goal is just to learn a collection of controller, we can also just create or run multiple gradient-based or evolutionary algorithm, like the normal evolutionary strategy algorithms that we saw in the first part of this lecture, in order to learn each of the solutions independently. Because we can just say, I want, in the fitness, you can say, I want solutions that reach this target point, and that's it. And that can become your fitness. And you can create or run an ES algorithm with different fitness in order to generate the same collection. But what we saw is that running a QD algorithm here, which was called back then BR evolution, for behavioral repertoire evolution, is actually significantly faster in order to cover the entire space than running independent evolutionary processes here, and that leads to even better solution, because what is interesting is that finding a solution that lead here during the random exploration of the evolutionary algorithm and QD might actually lead to solutions that are better for other tasks, like moving in a different direction here. So we show that not only it's a simple and effective algorithm, but it's also an algorithm that can accumulate some interesting stepping stones that will lead to better solution eventually. So that's what we say here, that learning all the solutions in one go is definitely more effective than learning them one by one. I already showed you some example of creative solution where the robot flip on his back and walk on his knee. So that's using Mapillity. And it's important to understand that this creativity of the solutions that can be found by Mapillity is not restricted to this specific example, but we observe this example in a lot of different applications. So for instance, here we use the Mapillity algorithm, and the goal was to learn how to push the cube in different directions on the table. And the behavioral descriptor that we use was the final position of the cube, because that was the diversity that we were looking for. And the fitness was the energy efficiency of the robot. So we wanted to be able to push the cube in different locations while minimizing the energy consumption. And because we designed this to be just a pushing task, we thought that we didn't have to include in the genotype the something to control the gripper of the robot. So that's why the gripper is forced in a closed position, and because of that, we do not expect the robot to be able to grasp the cube and lift it in the air. But again, that was before, or that was underestimating the performance of MapEdit, because this algorithm is very powerful and managed to find a way to block the cube in near the base of the robot and smash it from the top. And here's a second example, same thing, smashing the robot from the side in order to force the physical simulator to grasp the cube and solve the problem in a different way. So actually, we had this result because we made a mistake when we defined the BR descriptor, because we also included the z coordinate. We did not expect the algorithm to find it, so we thought that we just will have like one layer of the grid, but actually the algorithm managed to surprise us and find this solution. And that's a very good example, a second good example of the creativity of MapEdit, and multiple other approaches got quite interested in this creativity. And so that's why, for instance, MapEdit has been used by some researcher at New York University, for instance, to generate content for video games, like automatically generated content in video games, where we can use, for instance, MapEdit in order to design new level for Bullet Hell game. So it's a game where you want to control an agent, or the player controls the agent, in order to try to survive and not take all the bullets here, and that's a quite popular type of games. And so we can use MapEdit in order to generate diversity of scenarios, some of them with requiring a high dexterity, like here, but with also a high strategy, and some other low dexterity and low strategy, so different trade-off between strategy and dexterity required by the level. The author of this paper also increased or extended the MapEdit algorithm with some additional elements in order to manage constraint satisfactions. The same team actually also used MapEdit in order to generate dungeons in Dungeon Designer, so with an evolutionary dungeon designer, in order to help a video game designer in order to generate new content for their video games. So here you can see some example of design of the dungeons that can be generated by the algorithm. We can also use, so that was done by one of my former colleague and collaborator, Jeff Clune, who is now a team leader at OpenAI, where we can use MapEdit in order to generate some adversarial example to full neural networks. So typically here, they use neural network in order to, or they use a specific type of genotype in order to generate this kind of images, and they use a behavior descriptor that is the predicted label from a pre-trained neural network based on a very famous data set that is called ImageNet. So it's a neural network that is pre-trained on a classification task in order to recognize different objects in the data set. So it is typically to recognize obelisks, comic books, medicine chest, slot, car wheels, and a lot of different classes like bagels, school buses, and so on. So it's a very famous and challenging data set. And the fitness that they use in this experiment is a confidence level of the network. So typically in the classification data, in the classification neural network, as you know, you can use a sigmoid activation function at the output of the neural network that will give you the probability of each class, and the likelihood, or the higher the probability, the more confident is the network on this prediction. So if you have one of the class with value near to 1, the network is very confident about its output. And so here they took the label with the highest probability to define the BR descriptor, and the value of this probability to define the fitness. And then they use MapEdit to try to find initially they hope to have some artificial images that look well or resemble quite well to the expected labels, like a bagel, so we can see here. But they also realize that this algorithm managed to generate some very good adversarial examples, so solutions that completely fool the algorithm. And here we use some, they were trained with with some deep reinforcement learning algorithm. And so you can see that some generated image, even if the total average performance of all this solution here is higher than 99%, you can see that most of these solutions here are very far from being actual, like school buses or strawberries and so on. Even if we can understand why, we can see that actually this algorithm managed to find the right features to be present in the images in order to fool the algorithm. So if you want to learn more about quality diversity, we set up a website that is called qualitydiversity.github.io. That is a website, a community website gathering papers, tutorials, and libraries, open source libraries implementing diverse algorithm. And we found that in the last couple of years, 3 or 4 years, there are more than 100 papers with different applications of quality diversity, ranging from robotics, video games, logistic problem solving, designing new drugs, designing content generation for video games, and so on. So that's the conclusion of our lecture on quality diversity. And in the next video, a short video, we will just have some concluding thoughts about evolutionary algorithm as a whole compared to other approaches for modern problems. So I will see you on the next video for these concluding thoughts.